Welcome to Calc 3. This is section 14.5, surface area examples. So for our first example, find the surface area of S, where S is in the plane x, z is equal to x plus 2y over the triangle with vertices 0, 0, 1, 0, and 0, 1. So if we draw out what this looks like, 0, 0, 1, 0, and 0, 1. So this is the xy projection of our region here, our region R. So this is the line y equals 1 minus x. So if we're thinking about what our surface area is, our surface area can be described with the integral over the region. If we parameterize our surface, RU cross RV, take the magnitude of that vector, integrate that vector over the magnitude of that vector over the region, then we can find that surface area. So let's parameterize our surface R as a function x comma y, or excuse me, the vector x comma y comma x plus 2y. And so then Rx, so our u is our x here, is equal to 1, 0, 1, the vector. R sub y is the vector 0, 1, 2. So Rx cross Ry. Doing the cross product, we get -1, -2, 1. And this is a nice magnitude to calculate. So our magnitude of our cross product is equal to 1 squared plus 2 squared plus 1 squared is square root of 6. So this region we can nicely define as the integral from 0 to 1, the integral from 0 to 1 minus x, so doing our triangles vertically, our rectangles vertically at square root 6, dy dx. So this evaluates nicely to square root 6 over 2. And this is the surface area of that plane over that triangular region. So let's suppose that we have the surface area of the plane x plus y over the annulus, which is a disk with a hole in it, bounded by the circles with radius 1 and radius 2 centered at the origin. So our shadow looks like a disk with radius 1 and radius 2 centered at the origin. So we're dealing with circles, so we can think of polar coordinates. So our r ranges from 1 to 2. We think about our radius going from this point here, let's say this point here to here. That's 1 to 2 for our radius r. And our theta, since we're describing the complete circle, goes from 0 to 2 pi. So we can define our function, our vector r, not to be confused with our radius, as x, y, x plus y. To convert to polar coordinates, we can do either conversion to polar, or we can stay in our conversion and then do our polar conversion later. So polar coordinates, we could say, doing that conversion first, we would get cosine theta, sine theta, cosine theta plus sine theta, and then we could calculate there. Or if we stayed with our parameterization, r is equal to x, y, x plus y, we get that rx cross ry is equal to the vector 1, 0, 1 cross the vector 0, 1, 1, which gives us the vector -1, -1, 1. So the magnitude of this vector, magnitude of rx cross ry, is equal to √3. So since we're dealing with our region in polar, we can then convert our polar coordinates after the parameterization. So we can then say our parameterization looks like 0 to 2 pi, 1 to 2, of the inside piece, that's our magnitude piece, times r dr d theta. And this turns out to give us 2 pi times root 3 minus root 3 over 2, which gives us root 3 pi. And this will turn out to be the same function if you use your conversion to polar coordinates first. So sometimes it's easy to keep your conversion in Cartesian coordinates and then do your conversion later. So it's good practice to try doing problems in different fashions to figure out what works best when. But as always, if you have questions, let me know.